it is my pleasure to introduce the last speaker of the morning session of today. And it's going to be César Lozano from Oaxaca. And he's going to talk about birational geometry of two classical parameter spaces.
All right. Well, thanks for the invitation to this very beautiful landscape and a very broad conference. So, this being the last talk of a very intense morning, so I decided to keep all the details onto the rock. But if someone of you is interested in seeing actually the computations, I can totally show them. And but then for this talk, I will be basically showing pictures and trying to tell you what are the objects I've been interested in for the last year or so. And it is very nice that I'm not the only one using handwritten presentation after Paul's talk. I was feeling a little bit anxious. So if you get bored, which you might during the talk, so here I have an example for you. So what this is supposed to represent is a smooth quadric surface in P3. Nothing more classical than that. And what these lines are supposed to represent is the ruling, one of the rulings of this surface. So now, what I'm denoting here by QT is that suppose that you have a family of these surfaces in P3. It's your favorite family. So that it degenerates to a double plane. A double plane is nothing but the linear equation squared. And if you see if your family is nice enough that it degenerates to this double plane, as long as the quadric is smooth, you have a one-dimensional family of lines, right, of rulings. And what I'm asking is, if that quadric degenerates to this double plane, where do the lines go to? What's the limit of the lines? I'll come back to this question in a few minutes. But if you see something funny is going on, because if you naively say, well, the lines here will go to lines here, well, the plane has a two-dimensional family of lines, and here I have a one-dimensional family of lines. So there is some limit, some flat limit that needs to be computed here. And what I'm asking is, what's that limit? What's the family of lines in the plane that can be smoothed out to rulings of the quadric? Okay. So I'll come back to that question later on. So let me start by generalities. What's the bigger picture in which the problems I'm about to talk about fits in? So if you are given a moduli space X, something I didn't write here, and you want to understand the birational geometry of it, well, there are basically at least three things we can do. We can, if that moduli space comes to you as a GIT quotient, well, we can vary the polarization, understand the wall crossing for variation of GIT. Or you can just completely forget the moduli structure, that this space came to you as a moduli space, and run the MMP. So this second point will not remember a priori that the space is a moduli space, but it will give you all the information about the birational geometry of your space. And then the third point, which is not very clear at this point, but you can somehow vary the moduli functor. I will say a few things about this third point, but then if you vary the moduli functor, then you can analyze some wall crossing there also. So the outcome of these three processes are, well, in the first case, you understand some stable loci, and then what we get in many examples is that many different compactifications for that subset of stable points. So it is more or less clear what we understand by variation of GIT. We can understand the different compactification for the stable. Of course, the stable points will vary also, but sometimes they stay the same, but by different compactifications. Or if you just forget that it is a moduli space and run the MMP, you get birational models. Okay, and it's not so easy how to go from one point to the other, which is exactly what I want to do for this talk. I will show you two examples in which I'm playing these three descriptions against one another, and I can tell you something about the MMP. Well, anyway, I'll show you the examples. So let me go to the first one. I will start with a very classical object, and Paul said, the previous talk said, well, I'm showing you a very classical thing, going back to the physics. I'm going back to the 19th century with this classic picture. So what I want to parameterize I'm denoting here by U is a smooth quadric hypersurface in Pn. So this is a very simple-minded object. It's just a quadratic equation so that the partial derivatives don't vanish simultaneously, all of them. So that's easy enough. And if I take the coefficients of this quadratic equation, I can compactify this family U with projective space, right? It's going to be a big projective space of dimension this big N, which is a binomial coefficient. That's not surprising. Or I can, so that's a one compactification, one candidate for this X. Something else I can do is I can remember that these quadrics are nothing but symmetric matrices, and bilinear forms, of course, defined by this quadric equation, and symmetric matrices determine one another. So I can remember that, and then this space U is nothing but the quotient, this quotient SLN plus 1 model SON plus 1, and I can use tools described by Deconchini and Processi back from the 80s and construct the wonderful compactification of this family U. So what is that wonderful compactification? So very, very roughly speaking, the picture is, look for some irreducible representations of this SLN. And if you can construct a vector such that the stabilizer is SON, then the orbit of SLN will be isomorphic to the quotient, right? So the problem is actually finding that particular vector. And that's what they do in that paper. They actually tell you what's that vector so that the orbit is isomorphic to this. And then once you have the orbit in a big projective space, you can take the quotient. It's not a random vector. It's a very special and very particular one. But then the idea is to get this quotient inside some projective space, and then you take the closure. And then they prove that the closure, what they add when they take the closure is nice, normal crossing divisors, so on and so forth. So that's, and they call it the wonderful compactification. That's back from the 80s. So I won't say anything about this point of view, but it is, I'll keep it in the back of my mind because I'll come back to it. And instead of constructing a compactification for this U, using the wonderful compactification, these tools, I will go back to the 19th century and use basically a construction given by Schubert. We can find this description actually in this book by Schubert, in which he describes many things among these compactification and Schubert calculus and so on. So instead of, again, another simplification, I'm not doing the most general case. The most general case doesn't need an additional ideas. I think this n equals 3 contains all the ideas that we need. The more general case actually requires more computational skills, but not new ideas. So I will restrict myself to this case. So how do I construct a compactification for smooth quadrics, which is not projective space? Well, the simple-minded one is projective space, is P9, and of course I just take the coefficients. That's it. So this is, and if you see, this is an inclusion, so I can include this U inside this P9 and then take the closure, and that will give me just P9. That's a nice compactification of this U. Well, instead of taking Q, I can take this quadric. Since it is smooth, I can just associate the inverse matrix, right? It's going to be again symmetric. It's going to define another quadric. So this notation was a little bit unfortunate, but what I meant here is the dual variety of this quadric, the dual variety of a quadric hypersurface is another quadric, and that's all this is saying. Just associate to Q the dual hypersurface. Again, it's a P9, so this is not new information. But then here I can do something else. So think of Q as a surface in P3, and then think of all the tangent lines to Q. That will be a divisor in the Grassmannian of lines in P3. And actually, I'm denoting this divisor with this symbol, with this second order chalk variety. And that's again a quadric, a divisor of degree 2. So this will give me an element in this linear system. And then this is injective. Actually, all I'm saying is associate to QL a quadric-line complex, which is a very classical object. It's back from the 19th century again. And this is injective. So I can compactify this U by including it in this linear system. This is a quadric. This is again divisors of degree 2 in the Grassmannian of lines in P3, and take the closure. I can do that, or I can take the 3 of them. Here I'm not writing the linear system. This is supposed to be written here. I can take triples given by Q, the dual, and the quadric line complex. And this will be an inclusion. U lies in here. And now take the closure. And that's the compactification, basically, Hilbert constructed back in the 18th century. So now the example I wanted to tell you about is to run the MMP for these X. Of course, if I run the MMP for 9, I see nothing, I see nothing, and I see nothing. If I run the MMP on these individual compactifications. But I will see something for this particular one. Okay? So what I'm about to do is try to run the MMP on this X, which is a very classical compactification. All right, so of course, before doing MMP and all that, so I have these projections. I don't need the MMP to tell me that I can, once I have taken the closure, I can take the projection to P9, or the projection to the other one, to P9 dual, or the projection here to the linear system in the Grassmannian, or the previous ones, right? Instead of projecting all the way to P9, I can project to the first 2 factors, or or I can project to the second and third factor. What am I saying here? What I'm saying is that you can project to each of these factors, and what we will get is some diagram like this. And of course, here between these two, there is a birational transformation. That there's this diagram, which I'm not saying, but it is a flock. It's not very interesting, but here we get a flock between these two. So this is what we have. I haven't done anything yet. Not anything that's very special. So what I need, the ingredients I need to actually the MMP tell me something interesting is, so what is the effective cone and the net cone and the movable cone? The movable cone is the cone that contains all the small modifications of X. So the first 2 ingredients, and this this is written in the paper in general for any n, is the effective cone will be the exceptional divisors given by these projections for all I. So how many projections do I have? I have 3 projections in the case n equals 3. So the effective cone will be generated by 3 divisors. That's all I'm saying. And those divisors will be the divisors contracted by these 3 projections. But once I have these morphisms, I can pull back the hyperplane O1 for each of those, which is what I'm doing here. And that generates the ample cone. Okay? Easy enough. So what I'm saying here for n equals 3 is telling you that the ample cone and the effective cone is all encoded by divisors given by these 3 projections. So what I haven't done yet is the movable cone. What are the small modifications for this X? Okay? Well, one corollary of this computation is that x is Fano. X is Fano for any n, not for n equals 3. And what this tells me is that when I run the MMP will terminate in finite time. So this is good news. I can carry on and expect finitely many answers. Okay? So I will tell you what the small modifications are for this case. So here is the diagram I had already. This is an explicit description of the effective cone. And what I'm drawing here is that the effective cone is a cone in a three-dimensional space. And what I'm drawing here is a cross-section of that cone. And these are the generators. Okay? So this is a cross-section. And these subdivisions of this triangle are the Mori chambers. Of course, I'm not telling you how to compute this, but this can be computed. It's not so hard. So the Mori chambers decompose like this, and once I have this decomposition, I can totally see what's the movable cone. And the movable cone will be the ample cone, which is this shaded piece, and some other cone down here. Okay? So what I should expect out of this picture is that I have these edges will give me these contractions all the way to P9 dual, and this linear system, which is something like P20. But then I have something extra. Okay? And for this particular case, let me just tell you what's that something. This wall crossing, this flip here, how to construct that flip. If you take, how am I doing for time? Okay, so this x is again quadrics and some this special compactification I just told you about, and this is the Kontsevich moduli space of stable maps of degree 2 in this Grassmannian. So, and a point here represents a map of degree 2 to the Grassmannian. And if you see this map from P1 to the Grassmannian, each point represents a line. So what I'm saying is that the image of a map in the Grassmannian is going to give me a curve. And each point of that curve represents a line in P3. Then when the curve moves in the Grassmannian, the line will move in P3. And what I'm saying with this map down here is that that line sweeps out at the quadric surface. And of course, it is 2 to 1 because each quadric has 2 rulings. Okay? So, of course, this is branch along the cones when the 2 rulings merge into just 1 ruling. And so this construction is not very strange. This construction is take Q and associate to Q the Fano scheme in the Grassmannian. Okay? And what I'm saying is forget about the quadric and just remember the Fano scheme. And if you move the quadric, you can take the Fano scheme inside the Grassmannian and consider that Fano scheme as a superarray of the Grassmannian. And what I'm saying with this diagram is that those deformations actually are compatible. But the compatibility is actually on the level of the smooth members. Once these members start becoming very singular, then I don't know what to do, and then I need to flip. And that's basically the construction I didn't see by the classical projections into the quadric-line complex and the dual quadric and all that. So going back to my original question, so if you take a smooth quadric and degenerate into this double plane, what I'm saying is, well, this is remembering the rulings. And it was a very tricky question because before x, I wasn't able to tell you what's the limit. What I'm saying with this diagram, because this flip appears at the level of x and not at the level of P9, which is just remembering the quadric, that means that this limit actually remembers the family. So once you forget about the family, it's impossible to tell what's the limit. And the family is remembering in the fact that there is this circle here, which is supposed to represent a conic. So all the rulings of this quadric map to tangent lines of a conic. And the conic is actually information encoded in the family of the quadric. Okay. All right. So that's basically the geometry of the flip, and that's n equals 3. So just to show you that this is very hands-on. So what happens for n equals 4? When n equals 4, again you have a 4-dimensional space, and a cross section will be a cross section of that cone can be represented as something like this. So in that particular case, that's the effective cone, and then the ample cone will be some other polytope inside this one, and then I can describe the small modifications instead of the or subdivisions of these polytope, and I can continue with this for 5 dimensions and so on and so forth. But then, if I want to mimic the previous description of the quadric-line complex, instead of considering the Kontsevich moduli space to the Grassmannian, here I need to consider some Alexev moduli space of stable maps from P3 into the Grassmannian. Here I will have the Hilbert scheme, and then the whole project basically carries over for these higher dimensional analog. So implicitly what I'm saying is this very naive fact. Suppose that you have a quadric hypersurface in P. This is 2n plus 1. Well, that defines a quadratic form by tautological terms. And then for that quadratic form, I can look at all the subspaces that vanish on that form, and that will give me the orthogonal Grassmannian inside the Grassmannian. All the subspaces that vanish along this quadratic form. And what this diagram is telling you is that you can vary the coefficients of this quadric, or you can vary the subschema structure of this orthogonal Grassmannian inside the Grassmannian. And those deformations are basically the same, up to some extent, of course. Because then I need to flip and so on and so forth. But then this diagram is telling you something about these very basic geometric fact. That the orthogonal Grassmannian the orthogonal Grassmannian as a subschema of the Grassmannian can be understood as just varying the coefficients of the quadratic form it comes from. Okay. Now, so what is the observation after this example? That all the birational models that I've shown you for this particular compactification are again parameter spaces. This is a tautology after what I've said, because I have constructed the parameter spaces by hand. But then, is this a coincidence, or this reflects on more deeper structure in this for these spaces, for these moduli spaces? Remember that I was running the MMP for X, and the MMP a priori knows nothing about the moduli structure of X. So this is a nice coincidence. So what we're trying to understand, okay, so let's try to understand if this is a coincidence or if there is a deeper structure here. So what we should do is, what if we start with a family of stability conditions, which is varying the moduli contour, giving meaning to that, and see whether we can understand all the moduli spaces varying the stability conditions as birational models given by the MMP for some X. That would give meaning to the third point I started with, that instead of running the MMP, we start varying the moduli contour and try to make compatible this information with the instruction coming from the MMP. And that's basically what we do in another paper, which I won't say anything about, but this is an advertisement. And that we are able to do that for elliptic curves in P3. So we describe the stability manifold and the decomposition of this stability manifold into chambers. And it turns out that for that particular example, all those chambers actually correspond to running the MMP on the Hilbert scheme of elliptic vortex. That's what it's in this paper. Which as a matter of fact, I wrote this, submitted this morning, and we submitted the paper actually this morning. So I can safely say this has been submitted. It's been in the archive for about a month, and it's joint work with Patricio Gallardo and Benjamin Smith. And the example I told you about at the beginning of this talk is published in this paper, which you can find in the archive also. So those are the examples I wanted to tell you about. Thank you.
Have we got questions?
Just one question. So you get support to the conjecture that there is not a coincidence that
It's not a coincidence for this Hilbert scheme. Instead of starting with the MMP, we started with this variation of Bridgeland stability conditions, and we exactly get what we should have gotten with the MMP. So again, that's all we can say. Is there a deeper structure for these moduli spaces? I don't know. All I've seen is examples like this popping up.
Are you thinking of the elliptic curves as the intersections of two quadrics?
That's right. That's right. And actually, once you set that, one of the models that we get out of these Bridgeland moduli spaces is the Grassmannian of pencils in the space of quadrics. That's one of the models.
have you tried to see what happens if you put an extra structure on the elliptic curve?
Like what?
Or like level structure or something like that?
No. Actually, it is funny because we are able to write. Actually, that's a picture I should have brought with me. But if we are able to decompose the stability manifold into chambers, and many of those chambers don't modify the principal component of the Hilbert scheme. So don't touch the elliptic curves at all. Many of those chambers just modify this ghost component of the Hilbert scheme. The Hilbert scheme has two components: the principal component, whose general member parameterizes smooth elliptic curves, and some other component that parameterizes subschemes with the appropriate Hilbert polynomial. Wall crossing in this stability manifold many times modifies this other component, and we don't see that in the MMP picture. So besides, it gets very complicated. So the easy answer to your question is no. It is already complicated as it is.
Okay. Questions? So let's thank our speaker again. So launch, and then we'll resume at 16:30, I think.